Imagine standing beside a machine so powerful that a single push of its blade can move enough earth to fill several dump trucks in seconds. You hear the roar of a giant diesel engine, feel the ground vibrate beneath your boots, and watch thousands of kilograms of steel crawl forward like a mechanical beast. But here's what nobody tells you. Before a bulldozer ever shapes a highway, a dam, or an entire city, its story begins thousands of kilometers away, deep inside mines scattered across the planet. And what happens next surprised even experienced engineers. Most people see a bulldozer as just another construction machine. But think about this. Some of the world's largest bulldozers weigh more than 100 tons and contain over 80,000 individual parts working together with incredible precision. Their steel frames survive extreme heat, freezing temperatures, and impacts that would destroy ordinary vehicles in minutes. And this is where it gets truly extraordinary. The materials inside these giants have traveled farther than many people ever will. You might think bulldozers are born inside factories. In reality, they begin their journey in iron ore mines in Australia and Brazil, copper mines in Chile and Peru, nickel deposits in Indonesia, and chromium reserves in South Africa. Thousands of miners, giant excavators, and trains work around the clock to feed the global appetite for heavy equipment. Some raw materials travel more than 15,000 kilometers before reaching the factory floor. And that's only the beginning of a supply chain hidden from almost everyone. Mega projects depend on these machines more than most people realize. A single bulldozer can prepare the ground for airports, highways, ports, and even giant hydroelectric dams. Without them, entire cities would take years longer to build. Yet behind every machine stands a hidden global network of miners, steelworkers, ship crews, and engineers. And soon you'll discover how ordinary rocks transform into one of the toughest machines ever created. Everything starts with iron ore. Nearly 60% of the world's premium iron ore used for heavy machinery comes from Western Australia and Brazil. Giant mining trucks carrying more than 400 tons climb dusty roads, while electric shovels tear into ancient rock formations that formed billions of years ago. The ore often contains between 62 and 67% iron before refining. Most people never think about this, but a single large bulldozer eventually contains more than 50 tons of steel. After extraction, enormous freight trains stretching more than 2 kilometers carry the ore toward coastal ports. The sound of steel wheels echoes across the desert while clouds of red dust rise behind the locomotives. Bulk carriers then begin journeys of up to 10,000 kilometers across oceans toward steel mills in China, Japan, South Korea, and Europe. Imagine millions of tons of rock constantly moving around the world just to build machines that reshape the earth itself. But steel alone cannot survive the punishment of modern mega projects. Hydraulic cylinders, gears, and wear plates need chromium from South Africa, nickel from Indonesia and Canada, and molybdenum from mines in the United States and Chile. These special metals create alloys strong enough to withstand incredible pressure and constant friction. Without them, bulldozer parts would wear out years too early. And this secret recipe costs manufacturers millions of dollars every year. Copper plays another critical role. Mines in Chile and Peru produce high-purity copper exceeding 99% concentration after refining. Thousands of meters of wiring inside a bulldozer deliver electricity to sensors, lights, control systems, and starter motors. A modern machine may contain several hundred kilograms of copper, hidden beneath panels and steel structures. Yet very few operators ever think about the mountains that had to be moved to produce those wires. Rubber tells another fascinating story. Natural rubber used in seals and vibration dampers begins on plantations in Thailand, Indonesia, and Malaysia. Workers tap trees before sunrise, collecting white latex that later undergoes chemical processing. Synthetic rubber ingredients arrive from petroleum refineries in Saudi Arabia and the United States. Together, these materials create components that survive years of vibration, mud, heat, and freezing temperatures. Think about this. Producing enough steel for one giant bulldozer releases several dozen tons of carbon dioxide into the atmosphere. Mining operations consume huge amounts of energy, while ships and trains burn fuel moving raw materials across continents. Engineers now search for cleaner steelmaking technologies and alternative fuels to reduce environmental impact. But balancing performance and sustainability remains one of the industry's greatest challenges. One large bulldozer represents raw materials gathered from more than a dozen countries and transported across tens of thousands of kilometers. Iron, copper, nickel, chromium, rubber, and countless other ingredients converge with astonishing precision. But here's the mystery most people never see. How do mountains of rock and rivers of molten steel transform into a machine powerful enough to reshape the modern world? And this is where our journey enters the heart of the factory. The moment raw materials arrive at the factory, the transformation begins. Massive steel plates, alloy bars, hydraulic tubing, and electronic components enter a production system that never seems to sleep. Forklifts weave through aisles while overhead cranes carry loads weighing several tons. You hear warning alarms echoing through the building, smell machine oil in the air, and see sparks flashing in every direction. But here's what nobody tells you. The first step determines whether a bulldozer survives decades or fails within months. Everything starts with steel preparation. Giant furnaces melt recycled steel and refined iron at temperatures reaching approximately 1,650 degrees Celsius, or 3,002 degrees Fahrenheit. Inside the furnace, glowing liquid metal churns like a miniature volcano while impurities rise to the surface and get removed. The heat feels intense even from several meters away. What happens next turns that molten river into the backbone of a machine capable of moving mountains. The molten steel flows into continuous casting machines where it cools into enormous slabs. Rollers guide the red-hot metal forward at speeds between 1 and 3 meters per minute. The steel's surface glows bright orange, gradually fading to deep red as cooling water sprays across it. Steam erupts everywhere, creating clouds that fill the factory ceiling. Most people never witness a process that looks so much like controlled lava. Next comes rolling and forming. Massive rolling mills squeeze the steel under pressures exceeding several thousand tons, reducing thick slabs into plates with remarkable precision. The rollers spin at speeds reaching hundreds of revolutions per minute, while the steel stretches and reshapes before your eyes. The sound resembles constant thunder. Every pass through the mill brings the future bulldozer frame closer to life. Computer-controlled plasma cutters now take over. Superheated plasma streams reaching temperatures above 20,000 degrees Celsius slice through thick steel with astonishing accuracy. Bright arcs flash across the workshop floor while robotic arms follow digital blueprints down to fractions of a millimeter. The smell of heated metal fills the air. And this is where giant sheets begin turning into recognizable bulldozer components. Workers and robots then position these components for welding. Automated welding systems generate temperatures above 6,000 degrees Celsius at the arc while depositing metal bead after metal bead. Sparks rain through the air like orange fireworks. Some welds continue for several minutes, while critical structural joints require hours of inspection and reinforcement. A single weak weld could eventually bring an entire machine to a halt. Now the bulldozer frame enters heat treatment. Giant industrial ovens heat the steel to approximately 900 degrees Celsius, or 1,652 degrees Fahrenheit, for several hours. This process changes the internal crystal structure of the metal, increasing strength and durability. When the doors open, the steel glows faintly in the darkness. Engineers know that a few degrees too high or too low can affect years of future performance. Hydraulic cylinders follow a completely different journey. Precision-machined steel tubes enter honing machines that create mirror-smooth surfaces measured in microns. Hydraulic systems later operate under pressures exceeding 300 bar, or roughly 4,350 psi. Every surface must remain flawless because even tiny imperfections can cause leaks or premature wear. Most people never realize that a bulldozer's strength depends on extraordinary precision hidden inside these cylinders. Meanwhile, giant diesel engines take shape in another section of the factory. Robotic systems install crankshafts, pistons, injectors, and turbochargers while technicians verify every measurement. Some engine assembly stations complete one major unit every few hours. The smell of lubricants mixes with fresh metal surfaces as workers perform final adjustments. And this is where the machine finally gains its future heartbeat. Assembly now accelerates dramatically. Overhead cranes lower engines into completed frames while workers connect hydraulic lines, wiring harnesses, cooling systems, and electronic controls. Components weighing several tons settle into place with incredible precision. Every movement follows carefully planned sequences developed through decades of engineering experience. What looks effortless actually requires thousands of calculations and inspections. Then comes one of the most recognizable features, the tracks. Individual steel track links weighing dozens of kilograms each connect into continuous chains capable of surviving brutal terrain. Automated presses apply enormous force during assembly, while technicians verify alignment and tension. The metallic clanking echoes through the workshop. Suddenly, the machine starts looking ready to conquer landscapes. Next, the blade arrives. Forged from high-strength wear-resistant steel, this enormous component receives specialized coatings designed to fight corrosion and abrasion. Robotic paint systems apply perfectly controlled layers while drying ovens accelerate curing. Bright lights reflect from freshly coated surfaces. The bulldozer now carries the tool that will eventually reshape hillsides, roads, and construction sites around the world. Finally, workers fill the machine with hydraulic fluid, coolant, lubricants, and fuel before the first startup. The engine roars to life, sending vibrations through the entire building. Exhaust heat shimmers above the machine while hydraulic pumps begin circulating fluid through hundreds of pathways. After months of manufacturing, thousands of parts suddenly operate as one. But before this giant can leave the factory, it must survive tests that push it to its absolute limits. By the time a bulldozer reaches the testing floor, the machine already contains decades of engineering knowledge hidden beneath its steel skin. But here's what nobody tells you. Modern bulldozers rely on thousands of measurements and millions of lines of software instructions long before they ever touch dirt. You hear robots humming, laser scanners sweeping across metal surfaces, and computer screens constantly updating in real time. And this is where raw power meets astonishing intelligence. Everything begins with robotic precision. 6-axis industrial robots capable of repeating movements within plus or minus 0.02 millimeters handle critical welding and assembly operations. Their arms move with incredible speed and accuracy, completing tasks humans could never repeat thousands of times without error. Bright welding arcs flash across enclosed cells while sensors constantly verify positioning. Most people never realize that some robots work 24 hours a day with only short maintenance breaks. Laser scanners now inspect the giant steel frame. Green beams sweep across every surface and compare millions of measurement points against digital blueprints. Engineers monitor tolerances measured within tenths of a millimeter because even tiny deviations can create alignment problems later. The room stays almost silent except for cooling fans and the soft movement of the scanning equipment. What happens next surprised even experienced engineers. Artificial intelligence now joins the inspection process. High-speed vision cameras capture thousands of images every minute while AI software searches for cracks, surface defects, missing components, and paint imperfections. Some systems detect flaws invisible to the human eye. Rejection rates in advanced factories often remain below 2% because defects get caught early. Think about this. Machines now inspect machines with extraordinary consistency. Hydraulic systems undergo one of the toughest tests inside the factory. Pumps force fluid through the system at pressures exceeding 350 bar, or roughly 5,000 psi, while sensors monitor temperature and flow rates. Engineers search for microscopic leaks that could eventually become catastrophic failures. The hiss of hydraulic fluid and the steady vibration of pumps fill the testing hall. A leak smaller than a droplet can stop an entire machine worth hundreds of thousands of dollars. Then comes ultrasonic inspection. Technicians use sound waves to peer deep inside thick steel welds without cutting them open. Hidden cracks, trapped gases, and internal imperfections reveal themselves on computer screens in seconds. The process feels almost like medical imaging for giant machines. Most people never think about invisible defects hiding inside metal, but engineers lose sleep over them. Now the completed bulldozer enters endurance testing. Massive dynamometers simulate years of workload while engines operate under heavy loads for hundreds of hours. Temperatures climb, exhaust systems glow faintly, and cooling fans roar like jet engines. Sensors monitor vibration, fuel consumption, and component stress every second. Engineers know that if something breaks here, it saves customers from expensive disasters later. Some machines face brutal environmental chambers capable of reproducing conditions from -40 degrees Celsius to more than 50 degrees Celsius. Engineers expose components to freezing winds, desert heat, humidity, and dust storms. Ice forms on metal surfaces one day, while scorching heat surrounds them the next. What happens next separates ordinary machines from true giants of heavy industry. International standards play a critical role. Manufacturers follow ISO 9001 quality systems and strict emission requirements while documenting every stage of production. Barcode systems track components from raw materials to final delivery. Some factories store millions of records for decades. Imagine being able to trace a single bolt back to the exact batch of steel that produced it. But here's something machines still struggle to replace: human experience. Veteran technicians often detect unusual vibrations, strange sounds, or subtle imperfections before sensors notice anything unusual. Some specialists spend 30 years listening to engines and feeling hydraulic systems with their own hands. Their instincts come from countless hours on factory floors. And this is where human skill still beats machines. Finally, the bulldozer leaves the factory and heads to proving grounds that look more like battlefields than test tracks. Rocky hills, muddy pits, steep slopes, and endless dust challenge every system inside the machine. Engineers intentionally push these giants to failure because weakness discovered today prevents catastrophe tomorrow. You hear engines roaring across the landscape and see steel tracks biting into the earth with incredible force. But one mystery remains. Just how many of these giants does the world build every year? And which countries dominate this extraordinary industry? Think about this. Every year, thousands of bulldozers leave factories around the world. But most people never stop to wonder how enormous this industry really is. Global production of medium and large bulldozers exceeds 25,000 machines annually, supporting a market worth more than $40 billion. The industry directly and indirectly employs hundreds of thousands of workers, from miners and steelmakers to engineers and operators. And this is where the numbers become almost impossible to imagine. China leads the world in heavy construction equipment production, accounting for roughly 35% of global output. The United States follows with about 20%, while Japan contributes nearly 15%. Germany and South Korea complete the top 5, together representing another 15% of production. Imagine 5 nations supplying the machines that shape roads, mines, airports, and cities across the entire planet. Most people never think about this, but bulldozers have transformed civilization for nearly a century. The first tracked bulldozers appeared during the early 20th century, but the technology exploded after World War II. Machines that once relied entirely on cables and manual controls evolved into computerized giants with GPS guidance and automated systems. Over the last 50 years, engine efficiency, operator comfort, and reliability have improved beyond anything early engineers could have imagined. And this is where it gets truly extraordinary. Some of the largest bulldozers on Earth weigh more than 100 tons and generate over 1,100 horsepower. Their blades can push enough material in one pass to fill several family cars. You hear engines rumbling like distant thunder while steel tracks bite into rock with unbelievable force. What happens next surprised even experienced engineers. Did you know that some mining bulldozers consume more than 150 liters of diesel fuel every hour under heavy loads? That's more fuel than many cars use in several months. Another surprising fact is that a single giant track link can weigh over 50 kilograms. And here's the third shock. Certain bulldozer blades cost more than luxury cars because they use highly specialized wear-resistant steel alloys. The future of bulldozers looks dramatically different from their past. Engineers now develop autonomous systems, hybrid drivetrains, hydrogen engines, and AI-assisted earth-moving technologies. Some prototypes already operate semi-autonomously, using sensors and satellite positioning to improve accuracy and efficiency. Over the next decade, smarter and cleaner machines will likely reshape the industry once again. But one thing will never change. Humanity will always need powerful machines to build its biggest dreams. From ancient rocks buried beneath Australian deserts to glowing furnaces, robotic factories, and proving grounds filled with dust and thunder, you've witnessed the incredible journey hidden inside every bulldozer. Most people only see the machine pushing dirt, but now you know the truth. Behind every track, every blade, and every roaring engine stands an invisible army of miners, engineers, machinists, welders, programmers, and operators working together across continents. And perhaps the most extraordinary part of all is that these giants exist because human imagination refused to accept limits. The next time you see one of these massive machines carving roads through mountains or preparing the foundation for an entire city, you'll know that its story began long before the engine ever started. You'll remember the heat of the furnaces, the sparks of welding robots, the precision of laser scanners, and the countless hands that shaped every component. Most people never think about this. But now, you'll never look at a bulldozer the same way again. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.